Well, first, thanks for inviting me to speak in this joint seminar between Marseille and Moscow. I'm going to talk about my recently finished project on the infinite-dimensional Terstona theory and its connections to the transcendental dynamics. So, first, I want to tell a little bit about the structure of the talk. First, basically, it will consist of two parts. In the first part, I give you a brief overview of the project. In particular, I tell you about the motivation, which comes from holomorphic dynamics, tell you about the main theorem we have proved, and also, then motivate this theorem independently from the point of view of the Terstona theory. Then present the grand scheme of how the proof goes. Afterwards, I will try to highlight for you the main ingredients of the proof, maybe for rather, well, the simplest transcendental entire function possible, just for the exponential. So let me start. So first, about the motivation from holomorphic dynamics. So, well, in holomorphic dynamics, we are interested in iterations of holomorphic functions. So if S is a Riemann surface and F is a holomorphic function from S to S, then we consider the sequence of iterates of this function F and investigate what's happening in the long run. So, well, for me, I am interested in particularly in the case when our Riemann surface S is a complex plane, and then in this case, F is either polynomial or a transcendental entire function. And I'm interested in transcendental entire functions. So, a particular dynamical set I want to talk about is the escaping set. So basically, it's defined as the set of all the complex plane Z, for which the iterates of Z under F escape to infinity. So, So in holomorphic dynamics, we very often don't want to study just one function at a time, but usually we want to study the parameter spaces of functions and parameterized by some parameters in one or the other way. So, for example, well, the most important, the famous example of such a parameter space is a Mandelbrot set. So it's the set of such parameters C for which the critical value of the polynomial Z squared plus C is bounded under iterations. So basically, well, on this picture, the Mandelbrot set is depicted in black. You can see it. So there are many people are studying this set. It has a lot of interesting properties. Many interesting conjectures are connected to it. And well, in particular, people are interested in understanding the boundary of the Mandelbrot set. You can see it here. So, and one way to understand the boundary better is to study the complement of the Mandelbrot set. That is the set of parameters C for which the critical value of the polynomial Z squared plus C escapes. So, in this case, so every such parameter in the complement of the Mandelbrot set can be characterized by its speed of escape or potential, or in its combinatorics or external angle. Well, speed of escape is basically described how fast the the point escapes to infinity. So here on this picture, you can see some curves. They are called external rays of the Mandelbrot set. And so all parameters that lie on this curve, they have the same combinatorics, but different speed of escape. So that the parameters that on this curve that are closer to infinity, that they escape faster. So now you can ask, well, a question whether can we do something similar for the transcendental entire functions? And yes, indeed, we can. And this is the main result of this, one of the main results of this project. So, yeah, before switching maybe directly to the main theorem, let me show you, well, maybe the simple families of transcendental entire functions and explicit families that we will be interested in. Well, first of them is the exponential family e to the z plus kappa, where kappa is the parameter. Well, that's the simplest transcendental entire functions that can be. And then the family for which we prove the classification result is a family of composition of polynomial with the exponential. So, let me remind you that the singular values of transcendental entire functions are defined as closure of the union of critical values and asymptotic values of f. Well, critical value is just image of the critical point, and here is the definition of the asymptotic value of transcendental entire function. Well, if you are not used to the just let me draw. If you are not used to the asymptotic values, then, for example, you can for the exponential function, the asymptotic value is equal to 0. So that we indeed have a curve to infinity from minus infinity to 0, satisfying this condition. So yeah, in particularly for exactly any function in the exponential family, we just have the unique singular value kappa. So here you can see just a picture of how the part of the parameter space is structured for the exponential family. You can see that here it's much more complicated than for the Mandelbrot set, because it's no longer the union of all these curves called parameter S is no longer an open set, as in the case of the Mandelbrot set, you see. So, but they are joined in a more difficult topological object called Cantor bouquet. So, all these curves are parameter rays, and they correspond exactly to the parameters kappa, such that which escape under iterations of e to the z plus kappa.
Excuse me, Kostya, Cantor what?
A Cantor bouquet.
Cantor bouquet. Okay.
Yeah.
Mm-hmm.
So let me then switch to the main result. So so given a polynomial p and entire function f naught, which is composition of p with exponential, and assume it has exactly m finite singular values, and also given a list of m, well, allowable speeds of escape, given somehow, I will explain about how it works a little bit later, and each corresponding to a particular single value of f. Then, in the parameter space of f naught, there is a unique entire function g, such that each singular value of g escapes exactly as prescribed by this speed of escape and combinatorics. And conversely, every function in the parameter space such that its all singular value escape fast is one of these functions constructed above. Yeah, here I have a little bit maybe vague word allowable, but it's not really restricting the generality in this theorem. I'm just sweeping under the rug some of the details that at the moment there's no need to present them because these are technical details. To prove this classification theorem, we use something that we call infinite dimensional Terstona theory. So this infinite dimensional Terstona theory is inspired by the classical Terstona theory in dynamics, or more precisely by the Terstona's topological characterization of rational functions. So this theorem about rational functions. So one says that a post-critically finite branched cover in F is Terstona equivalent to a rational function if and only if there is no Terstona abstraction. So here you, well, maybe I should give explanations about the definition. So the post-critical set of this topological of the topological branched cover in F of the two sphere is simply the closure of the union of the orbits of critical values. And the map is called post-critically finite if we simply have if the set PF is finite. So in a way, this theorem says that given a topological branched covering, just topological object, then if some topological condition holds, then this function is equivalent in substance to a geometrical object. That is a rational function which acts on the Riemann sphere, no longer just a topological two-sphere. So, and now based on this theorem, we can ask like a simple-minded question: what's happening if this set PF is infinite? So can we do something similar? So the answer is yes, and this changing from finite to the infinite setting leads to, well, completely different theory as it turned out. So well, first thing you should think about is that when this post-critical set is PF is infinite, then we already have might have topological branch covering of infinite degrees. So we have many more many more combinatorial models of the covering that we can try to represent as some holomorphic functions in some sense. So that's but well, let me remind you that we want to prove the classification theorem, and so we consider only very special branched coverings that somehow model the transcendental entire functions with finitely many singular values, all of which escape, such that these functions model exactly the speed of escape and combinatorics that we want to realize via a transcendental entire function. So, so and then this, as in the classical theorem, this set, this map F, which is in our case will be a quasi-regular branch covering, it defines the sigma map acting on the Teichmüller space of C with with set PF removed. So if somebody needs a reminder what is the Teichmüller space, I will give you.
Yes, I need. Yes.
Yeah, okay.
I don't remember very well.
So the Teichmüller space, in fact, there will be one more reminder a little bit later, but let me, so the Teichmüller space TF is the set of quasi-conformal homeomorphisms phi of the complex plane modular equivalence relation of isotopy RL PF and post composition with affine map. So yeah, so I will say a few more details a little bit later during the presentation about it, but at the moment you can just think that this is a special metric space associated to the Riemann surface C minus PF. So, and then here, as in the classical theorem, it turns out that this map sigma has a fixed point in the Teichmüller space, and this fixed point corresponds to the transcendental function with singular escape in dynamics exactly as we want. So, well, it's not at all obvious why this should be true. So it's theorem. So, in fact, to prove the classification theorem, we are interested in fixed point of this special operator sigma. Let me just tell you about the grand scheme of the proof, and then we switch to the second part of the talk when everything should be even more understandable. So how do we prove the classification theorem? So somehow we first we define a quasi-regular branch covering that exactly models the desired singular dynamics that we want to realize via transcendental function. So and then using this map F, we can set up a special operator sigma on the Teichmüller space of C with PF removed. Second, we then construct a special compact subset in the Teichmüller space, we call it CF, that is invariant under sigma. First, we prove that the restriction of sigma on CF is strictly contracting. And finally, we prove that there is a unique fixed point, and of sigma in CF, it corresponds to the entire function that we want. Well, to prove that it has a unique fixed point is not difficult. We just use 2 and 3, and basically the Banach fixed point theorem to argue that there should be at least one fixed point. But well, proving that this will be entire function that satisfy the required dynamics is a little bit well, this requires some proof. But again, it's somehow intuitively intuitively this should be clear, because the fixed point of F yields the map, the transcendental function, which has some sort of similar combinatorics as the map F. So out of these 4 items, the most difficult is item 2. So, and here's where all the challenges lie. And so during the next part of the talk, I'm going to tell you a little bit about 1 and 2, based on the example of the for example, of the exponential family. So it's the simplest one you could get in principle. Even though conceptually it's not much easier than the general case. So let me first tell you a little bit more about the escaping. Yeah. Are there any questions so far? So that before we switch to the second part. Okay, then we switch. So now you can forget about more general families like composition of polynomials, exponential, and consider only the family e to the z plus kappa. So, well, it's known result that the escaping set, it's well known and told the result by Schleicher and Zimmer, that the escaping set of any family of any map in the exponential family is organized via dynamic rays and in particular via ray tails, so you might say so. Then one would need definition of a ray tail, which I wrote here. So the ray tail is a curve R from t to infinity into the escaping set, such that for all n, if the iterates of this curve are injective, and with one endpoint is always at infinity, and so the rays converge uniformly to infinity. So in fact, you have some curve R, then under F, so it is mapped to some curve F of R, and then well these are all curves from a finite points towards infinity, and well they converge to infinity uniformly. So it's Fn of R. So everything converges to infinity.
Excuse me, Kostya, such rays also exist for polynomial maps, right?
Yes, but yeah.
So for this point, there is no difference between polynomials and transcendental maps.
Well, difference is different. That for polynomial, you in fact have these curves are union of these curves form the open set. But here
the
these
what
are
set, form what set?
Open set.
So open set. Yes. Okay.
Yeah. But here in this case, this union of the whole escaping set is the union of curves. It's not open. So yeah, but you're right. This is a direct analogy to the polynomial, in the sense that we can see these curves. Even though they are organized in a more peculiar way.
So difference is that in polynomial situations, the union of these curves is an open set, and here the union of these curves is in fact a union of countably many curves. Is this right?
Yeah.
Okay. Thank you very much.
Well, if you consider all possible ray tails for because there are many of them. So then let me tell you. So this was a more general definition for the ray tails of transcendental functions. It's exactly the same. But now should tell you a little bit about the properties of ray tails of the exponential map. So first, there are properties 1 and 2, which tells you basically that first this as t tends to infinity, the real part of the ray tail tends to plus infinity, so you have it organized somehow like this. So second is that, let me denote this by a note. Second property tells you that these ray tails have very precise asymptotics for the imaginary part. So A1, let me do 2 pi I S1. Here, for example, it's the same. So, and this, basically near infinity, these ray tails are basically straight lines, almost straight lines. And further, for every point which belongs to a ray tail, we know the very exactly the asymptotics of this point. So, in fact, let me have wrong IISN. So the asymptotics of this point, this is AN, is a very precise. So we can describe it by Fn of tau. If the iterates of some a special function f plus 2 pi I S n. So we really have the asymptotics for this points A0, A1, AN. So let me, if I have this defined, so AN is Fn of A0. So these are the iterates of some particular point of the end point of this ray tail. And also condition 4 means that our rays, they escape to the right faster than they might escape up or escape down. So then the external address of the ray tail is just a sequence of integers. We take them from this asymptotics. And potential is this number tau. Then this is exactly the combinatorial information that we take from the classification theorem. And now we want to so far this is just some arbitrary point in the escaping set of this function e to the z plus kappa. Our question is the following: so can we find another function e to the z plus kappa 1 such that its singular value escape also is an endpoint of a ray tail and having the same potential and having the same external address. That is, we for this function we have exactly similar pictures via array tails, and the new array tails have exactly the asymptotics given by S0, S1, and Sn, and we have precise asymptotics on the real part. So this is our problem that we want to solve. Well, so far so good. Now we switch to the Terstona theory.
Excuse me, Kostya, this what? We want to describe this asymptotics in terms of what?
So let me. So we the asymptotics is described via this expression fn of tau plus 2 pi I Sn, and tau is exactly the same number. It's called potential. So in fact, we want to have to find the transcendental entire function, the new e to the z plus kappa 1, for which its singular values have the following asymptotics, and it's the endpoint of the ray tails that have asymptotics prescribed by this external address. Is it answering the question or not clear enough?
Yes, yes, perfect. Yes, thank you very much.
Yeah.
Yes, perfect. Thank you very much.
Okay, so now we, okay, and well, maybe from this slide you should keep in mind exactly this picture where we have this sequence of ray tails that are iterates of each other. So now we want to set up the Terstona iteration. So basically, what we do is that we choose some function in the family e to the z plus kappa for which its singular value does not escape. Then, well, it's no, it's an easy lemma that then for this function all possible combinatorics and speed of escape are realized by some function z. So let me, okay. So let me draw this again. The right color. So this is a naught. U1. EM. Yeah. So and this is V, the singular value. So somehow, we want to construct a quasi regular function f, which models exactly a transcendental entire function for which its singular value escapes with the same speed of escape at combinatorics as the point A naught here. So what we do? We construct a special quasi-conformal map called capture. How is it defined? So first we construct simply connected domain U, which contains V, and simply connected Jordan domain U, which contains inside of it points V and the point A naught, and which does not intersect any other ray tails. And then we consider the map called a quasi-conformal homeomorphism of C called capture. So it's called, let me capture. And it is defined in the following way. 1, C of Z is equal to Z if we are outside of U. And second, C of V is equal to A naught. So, and then our quasi-regular map F, we define it to be equal the composition of this capture with F naught. Well, you remember F naught is our model, is our function in the family, which is good, which contains all possible singular escaping dynamics. Then for this function F holds the following property. So if this, let me introduce another notation. So this ray tail is called R naught. This ray tail with endpoint N1 is called R1, and the ray tail with endpoint RAN is called Rn. So we have f of Rn is equal Rn plus 1. This is exactly, and so the dynamics on the rays exactly coincides with dynamics of F naught on this ray tails. So in fact, this function for this function F has the singular value A naught, and it has exactly the required combinatorics. So in fact, we constructed a quasi-regular function that models the escaping dynamics the singular escaping dynamics that we want to realize. Well, the problem now is that we are not interested in the quasi-regular functions that realizes this dynamics, but we want to find the entire transcendental function that is doing this. So for this, we would need to define a special operator on the Teichmüller space. Before doing this, let me maybe remind you what are the quasi-conformal maps, because I'm using them also here very well. So for quasi-conformal, well, as you remember that conformal functions are mapping infinitesimal circles to the infinitesimal circles, basically. And quasi-conformal maps, what they do is that they map infinitesimal circles to the infinitesimal ellipses. And usually we don't even say just quasi-conformal, we say a quasi-conformal map, and K is a parameter that says that this ellipses cannot be too oblong. So we cannot, if we have a K quasi-conformal map, we can we get ellipses of some bounded eccentricity, and this eccentricity is bounded in such a way so that we cannot get something too long like this. So, and well, maybe this certain like quasi definition of quasi-conformal maps, but what you indeed will need for this talk to know about the quasi-conformal maps is the following intuitive thing. Let me check the font, the color. Okay. So if you consider isotopy of a quasi-conformal maps, fixing, for example, fixing 0 and 1. It's 0 and 1. And then you consider, for example, points x and y. They might coincide with 0, 1 or not. Then under this isotopy, many things can happen. So x might rotate around y, so it might get closer to y. But the point is that when we have this bound via k, then we will have also a bound on how close x can come to y under this isotopy, and how many rotations x can make around y. So in a way, this bound on KQC maps somehow bounds the amount of twists of and amount. So it bounds. It makes well, it bounds the amount of twists. Somehow give some rigidity of what can happen in the isotopy type. So. Yeah, and this is well, one of the reasons why one want to consider the Teichmüller spaces. So the Teichmüller, we are interested in the Teichmüller space of C with PF removed. Well, as you remind you that PF is just some escaping orbit, A0, A1, and so on. So basically, our Riemann surface is a sphere with infinitely many punctures or infinitely many removed points, and these punctures they converge to infinity. So the Teichmüller space of TF is or Teichmüller TF of this Riemann surface is set of all quasi-conformal self-homeomorphisms of C, modular composition within a affine map, and isotopy relative to PF. So, and what you need to know about the Teichmüller space for this talk is that there is a special distance called Teichmüller distance on TF, and equipped with this Teichmüller distance. TF is a complete metric space. So. Yeah, this Teichmüller distance, well, maybe it's not important for this talk, but Teichmüller distance is given exactly using this bound K, quasi-conformal dilatation. So in fact, well, the bounded subset in the Teichmüller space means that our isotopy types of quasi-conformal homeomorphism, they cannot somehow twist too much. There is a bound on what can happen. So, so good. Now we want to define an using our map F. Let me remind you. So we defined it here. So this is map F. Using this map F, we want to define the iteration on the Teichmüller space. It's happening in the following rather standard way, exactly as is in the classical theorem by Terstona. So we consider so sigma is a map from the one point in the Teichmüller space to another point in the Teichmüller space. So as you're points in the Teichmüller space are equivalence classes. So and phi is just one quasi-conformal representative of this class. So we take a quasi-conformal representative phi, then compositions of phi with F define a complex structure via just system of neighborhoods here for this Riemann surface, and then from simply the uniformization theorem, there is a uniformizing map phi tilde from this set with a new complex structure to the standard Riemann sphere. Well, then by phi tilde we take as the representative of the image of sigma. So, and in particular, on the right, this map, if we go around the diagram like this, it will be a transcendental entire map. So it is easy to check that this is indeed well defined on the Teichmüller space, not only on the level of on the representatives, because well, these maps F and G are simply the universal coverings of the punctured plane. So, and also, well, since we know that it's a universal covering of a punctured plane, we can write more or less explicitly that this function looks like A1 composed with exponential and with A2, where A1, A2 are affine maps. So the whole point of this is that if phi is a fixed point of sigma, then G has the same I take in quotation marks, the same singular escaping dynamics. So in a sense that first phi okay, phi of A naught, which is a singular value of G, it escapes, and second, phi, since this is a fixed point in the Teichmüller space, then phi will be equivalent to phi, isotopic to phi tilde relative to the singular set PF. So it really induces the same combinatorics of the covering. Yeah, from these considerations, it's not at all obvious why this function G would then also give exactly the same combinatorics from the point of view of potential and speed of escape, but it's sort of natural to understand it. So, but it's something that requires more proof. So next thing is that we, in our case, we don't want to do the Thurston, since we want to find only one fixed point. Might be that why we don't want to do the Thurston iteration on the whole space. Instead, we restrict our Teichmüller space to the set of so-called identity type points. So, well, it's good because it's invariant under sigma, and this identity type points are represented by quasi-conformal maps phi, such that they can be isotoped to identity in such a way that on the post-singular set, the map phi u tends to infinity, tends to identity uniformly in U, so that somehow for points with low indexes, the points under isotropy might somehow do some strange things here. Something might happen, but if the points have high indices, indices that they just move just around themselves. So basically near infinity, nothing is happening. So we somehow look, we have two parts. One part is are points with low indices where it's more chaotic, many things might happen. And second part for points, it's a complement of some big disk, where is a set where nothing basically is happening under the isotropy. Yeah. And then if we restrict sigma to this density type map, so then the advantage of this is that the map G that we get from the Terstons diagram has a very precise form. It's just e to the z plus, it's just translation of the exponential by phi of a naught. So in fact, we somehow recover the we indeed have the simplest possible form of this function. Second thing, okay. Wait a moment. Yeah. So, okay. And one more thing I wanted to tell you about is that under the identity type map, so that we have the following very nice property. So if this is Rn, this Rn plus 1, these are the ray tails, then using this formula, we get the following expression. So phi hat of Rn is equal to the logarithm of phi of Rn plus 1 minus phi of a naught. And so here we don't really there's only not very clear things think of how to recover this phi hat on the ray tails, is at which branch of the logarithm to take. But since we know that we are working with identity type maps, and we know that this set is invariant, then it simply follows that the ray phi hat of the ray tail phi hat of Rn must have exactly the same asymptotics as Rn. So this is, so in a way we have, using this combinatorial information, we can simply recover phi hat of Rn from phi of Rn plus 1, just knowing the external address. So, and this is allows to somehow obtain a simpler description of the for the homotopy information of points in the Teichmüller space. So first, let me, so you remember the pictures that we are working on, that starts from A0. We have this sequence of ray tails, and we call the union of these ray tails, this R0, R2, or R1, and so Rn. We call them the standard spider S0. So the spider is called, the spider is simply the image of the standard spider under the identity type map phi. So why why do we need them? So it turns out, first we can define the equivalence relation of the set of all spiders. So two spiders are equivalent if their endpoints coincide. The endpoints with the corresponding indices do coincide, and also coincides the homotopy type of every ray tail, which we call lex, in the complement of the phi of PF. So that and we claim that this information is enough to encode the homotopy information in the Teichmüller space. So yeah, so proposition that equivalent spiders correspond to the same point in the Teichmüller space. So that instead of having our quasi-conformal map phi, we can just consider the spider and where we just need to know the positions of the endpoints and the homotopy type of each leg, and this is enough to know, to recover exactly the point in the Teichmüller space. So it's like a simpler representation. So, and another thing is that it allows to do is exactly the spider algorithm. So knowing this equivalence class of a spider provides enough information to do the whole Terstona iteration. And this simplified Terstona iteration, we call it spider algorithm. So basically what's happening, we want to recover recover phi hat from phi on the ray tails or spider legs. Well, we know the explicit form of our map. So we simply just take the logarithm of Rn plus 1. So let me phi hat of Rn, let me rewrite this formula, is equal to the logarithm of phi of Rn plus 1 minus phi of A naught. So, and since we know the external address, that is this asymptotics of the ray tails, we can choose the right branch of the logarithm. So yeah, so I'm already talking for an hour, so I should somehow converge the time to the end of the talk. Let me only tell you one more thing about how exactly we construct the invariant compact subset. So on the level of spiders, okay, being in a bounded identity type subspace of the Teichmüller space means intuitively the following. So the distances between points n, so it's here not even a node, but it's phi of a naught, phi of a1, phi of in. So they are bounded below, so the points cannot come close to each other. And second one is that the spider legs, they cannot wiggle too much, so you cannot get something too crazy. Otherwise, you might escape in the Teichmüller space. So using this intuition, we can construct the invariant compact subset in the Teichmüller space. So it's happening for the case of exponential, we need 4 conditions that to do this. So first condition is basically means that the points with low indexes are always in some big disk zero. And the second condition means that the points with high indices have a really very precise asymptotics outside of zero. Let me show you the picture so you don't look here for the moment. So we have this big disk zero, right, and some smaller disks around our punctures. So under the isotopy of identity type maps, the points that are here that might wiggle, but they have to stay inside of zero. And these points have to stay in small disks around themselves. Then the condition 4 basically means that the points in let me show you closer. So it's some special estimate. You don't need to understand for the moment its precise meaning and why exactly these coefficients we are using. But this means that the points inside of this big disk row cannot come very close to each other. So it's well, it was natural. And condition 4, well, it's given in some special form. We need to give somewhat more definition to say precisely what it means. But roughly speaking, this means that the spider legs corresponding to points inside of zero, they cannot wiggle too much. So it just makes one rotation here, or makes one rotation here, and that's all. So not many things can happen. And then let me, for example, tell you in just 1 minute how exactly conditions 1, 2, 3, and 4 for phi hat follow from conditions 1, 2, 3, and 4 for phi. So, well, the first condition, since we have a very precise formula, so we have phi hat of an equals to the logarithm of phi of an plus 1 minus phi of a naught. And so you see, the first condition simply gives you, since we take logarithm and we have a bounded absolute value, so it gives you estimate on the real part from above, on the real part of phi hat. Then condition 2, condition 1 and 2 for the first point outside of the disk zero gives you estimates for the real part of phi hat. Then condition 3, since it bounds from below the distance between points, and in particular the distance between points an and point a naught, which is a phi of a naught, which is a singular value. So it gives you bounds from on the real parts from below. Well, this coefficients, their bound wigglings of the ray tails around other punctures, in particular around bound wigglings around a knot, which is a singular value. But since we have this precise formal logarithm, this exactly gives you bounds, since we take logarithm, on the imaginary part of the new point an, on the phi of in. So in fact, we somehow, using this estimate, we prove that our images will be contained in some square inside of this disk 0. This is how a part of this argument goes. So let me then wrap up and come to the conclusion. So, well, generally, the project is about the classification of transcendental entire functions of the form P of that are compositions of a polynomial with an exponential, for which all singular values escape on disjoint ray tails. This is given in the classification theorem. So the key to the proof is to develop an analog to the Terstona characterization theorem, but for singularly infinite case, well, and in fact the case of the topological covering of infinite degree, and this involves iterations on infinite dimensional Teichmüller spaces. So the point is that we can restrict. We don't need to consider the whole Teichmüller space, but we need to first restrict to the identity type maps which produce and identity type points of the Teichmüller space, and this reduces this more difficult Terstona iteration on the whole space to the so-called spider algorithm, for which we just need to know the endpoints of spiders, where the points of spiders are placed, and the homotopy types of curves. Okay, yeah, that's what I said. It is much easier to to estimate this homotopy information that is changing under the Terstona iteration using the spider legs. And yeah, and the invariant compact subset is given via some explicit bound on the position of the endpoints of the spider leg, and the some homotopy estimate on every leg, on how many times it can wiggle. The techniques are basically, we think that they can be applicable in a bigger generality, and one can try to, for example, the first candidate would be, not the first, but the reasonable candidate would be the transcendental entire functions of finite type and finite order. So in particular, because it's this is almost the biggest family of transcendental entire functions, for which almost all points escape on ray tail, so that we can again have this spider algorithm. So yeah, based on this project, there are already 2 papers on the archive, and in a few days you will see 2 more there. So if you're interested, you can check. So, and yeah, that's all. Thank you.
Okay, Konstantin, thank you very much. Are there any questions?
Yes, excuse me. So the question is, Kostya, your result seems to have quite general form, but at the same time it is only formulated for one very specific family. What is the next level of generality where you would like to get it?
Yeah. I mean, okay. So I mentioned it here. So I would like to proceed maybe towards functions of finite type and finite order, because this is the case when we can make use of this ray tails. Well, the reason why at the moment
excuse me, you said this, but Kostya, excuse me, you said this, but already even you see finite type and finite order. Okay, let's say order 1 and type 1. Already it's more than exponential function. I mean, there is. It's not. I mean, there is. How do I say? There is a clash between what you prove and what you say, what you conjecture.
Yeah. Let me then answer why I didn't do it immediately for this case, but rather for the exponential. One reason is that then you don't have the explicit description of the parameter space of these functions. Here, for example, for the exponential, you have polynomial of exponential. It's one, the way it's a polynomial. It's much easier to get estimates on how this polynomial will change under the when we move in the parameter space. But for more general types of functions, this requires additional machinery to be involved. And second thing is that here, for the functions which are positions of polynomials and exponentials, you can indeed have this description, nice description of escape in dynamics via potential and external address. So for more general families, it works a little bit more complicated. So there you still have well-defined external address.
What is more complicated? Can you say what?
For more general families.
What for more general families?
This description via external address and potential. So you don't have it that explicitly. Like external address you do have, but for the potential you need to consider it on a little bit different level. You don't have really this precise number and then this precise asymptotics. So it's in principle it's possible to do this, but it requires better understanding of parameter spaces of more general functions. That's I still don't have it. But perhaps it might be that for more general families of functions, we get then less precise results. So here we know more about functions and we get more precise results, more precise formulation of this theorem. And I'm not sure that it can be given that nicely for more general families of functions. So it's both feature and flow.
Okay. I see. Okay, thank you very much.
Okay, are there any more questions? Okay, so thank you, Konstantin. And for the Russian part of the audience, the next seminar will be in 2 weeks. Obviously, seminar on May 3 is skipped. Well, maybe even not in 2, but in 3 weeks. We'll inform you by mail whether we have a seminar on 10th of May. Okay, so see you that time in Zoom, if another is not specified in the email. Okay, thank you.
Okay, thank you for coming. Bye.
Bye.